switch to English. First of all, we're talking about natural language processing, and second of all, it's, so you can tell it's my native language. Before I get started, just a little bit about who I am and what I'm doing here. My name is Ari Bornstien. I'm an open source engineer focusing on AI, NLP, and a little bit around computer vision and machine learning at Microsoft. I work and focus predominantly with communities and startups here in Israel. And our focus is to develop open source tooling to help unblock communities and to identify what are some of the interesting technological gaps to help make you guys successful. So if you guys have ideas for projects or anything interesting, feel free to speak to me after the hack or later throughout the course of the day. And the goal for that is to, sorry. Every once in a while, you need a good picture, especially when it's Microsoft and open source. Yeah, sorry. All right, perfect. Can you hear me better now? All right, perfect. Thanks. So a big part of why we do this investment is because we want to take the learning and the expertise and the ability to unblock some of the stuff we're doing here in Israel and also scale it internationally. So that's also a big part of what I do is after we work on projects and get them open sourced, I write content online, and I also travel to different knessim around the world, here's in China, and try to share some of the learnings. So enough about that. Let's get to why everyone's here. How many people here, by the way, are working on the Microsoft Challenge? All right, solid amount, awesome. Before I get started, I want to kind of talk a little bit about some of the milestones that Neural has brought to NLP. And a lot of the things that have improved and have become a lot more practical or capable are things like sentiment analysis, the ability to take a sentence and be able to determine whether it's positive, negative, which is interesting. This as well, I think for me, this is one of the ones that I think is most interesting is machine reading comprehension. So around being able to process texts and then answer questions around them related to Q&A. So for instance, I don't know how many of you guys can see it, there's a text here, a short paragraph about Nikola Tesla, and then you can ask a question, what city did Tesla move to in 1880? And the system can identify where in the text the correct answer is, and it knows it's Prague, which is pretty incredible. Again, not fully baked, but it's something that even 5-6 years ago we would have thought is mere science fiction in the field of data science and machine learning. Another area where we've made a lot of progress is in natural language inference, the ability to tell whether two sentences entail each other, contradict each other, or neutral. This is something on first glance it might seem a little boring, but it's something that's critical and fundamental for many Q&A and information extraction algorithms. Typically, we have algorithms that are really good at getting a lot of candidate answers, and you'd use a lot of these inference systems or this implicit understanding of inference to be able to identify or filter out what's the actual correct answer to a given query. And the other one that you guys have probably seen directly, I know specifically, but like it's someone who's an Ole, who Hebrew is my second language, the improvement in terms of neural machine translation has been great. Yes, sorry. The improvements in translation are a huge thing. So what are part of the advances that have enabled that? Well, so a lot of it has to do is how we represent text. So just before I get started, most of you probably know what are word vectors. Who doesn't know what a word vector is? Don't worry, I won't allow you to. All right, so we have a couple, so this is great. So essentially, word vectors are a way of representing individual words or text as a numerical vector so that we can process it. And traditionally, we used, most traditional machine learning algorithms used a representation called bag of words. What that meant is you would take a large corpus of text and you would run through all of them, and you would take, given on the individual piece of text that you're processing, you would have a binary vector for each feature saying, is this word in my corpus or is it not? And then I'd have a vector, a very, very sparse vector, and maybe I could try to reduce that vector, and I would use that for language processing or whatever my task would be. In addition to that, you might apply some statistical algorithms like TF-IDF, term frequency, on top of that. So I might give different weightings to these different one-hot encoded, or these different one-hot encoded bag of word vectors based on how often they appear across the different documents of my corpus to more even out the weighting. And later on, we built on top of this with this concept of distributional embeddings. And I think this is a concept that's extremely fundamental to understanding the progress and development of word vectors, because it's a common misnomer or a misunderstanding that a lot of people believe that word vectors were created with the advent of word2vec. But a lot of the insight and the techniques we had actually existed during this period of distributional embeddings. And what a distributional embedding essentially enables you to do is within your entire corpus, there's this fundamental concept. There's a famous quote by a man named Firth that says, we understand the meaning of a word based on the context that it appears. When we use a bag of words approach, we're taking an independence assumption between each word. In a distributional embedding system, we essentially encode each word by having a vector of either frequency counts or co-occurrence counts of all the other words that it appears with. And over time, and this was where traditionally a lot of, when we dealt with word vector representations, a lot of the research was traditionally done in NLP, is how do we create these embeddings? What window do we use? We saw that frequency by itself doesn't necessarily work as well. So do we use structural paths? And this was one of the foundational methods. Now, the challenge with this is it was very computationally expensive to create these things. A lot of dynamic programming, a lot of complex feature engineering. And so where Neural helped change the game with the advent of word2vec and skipgram is it allowed you to essentially train a similar concept of representing context within the understanding of how we embed the meaning of a given word without having to run it across each individual corpus. We could train and transfer some of this information by training on large amounts of textual data. And the two first algorithms that worked for this were CBOW and skipgram. How many people here know what the difference between CBOW and skipgram? Okay, so about half the classroom. So for the other half, the main difference is I always sometimes get them backwards, but essentially one of them enables you give one word and you try to predict based on that word what are the words that surround it. I believe that's CBOW, that's skipgram, yeah. It's skipgram? And then CBOW is the opposite way around. I give you a cloud of words and you try to predict which word's in the middle. And by training a model on this task, I learn a representation for each word that embeds some contextual information. So that was where a lot of progress happened about 2, 3, 4 years ago, and everyone went crazy and said, look, all those advances we had before, we're in really, really good shape. Things are solved. We built on top of these, so we have things like glove vectors, which one of the challenges we saw with skipgrams is that they're really good at encoding local context, but when you start to deal with global context across large corpus, it struggles. So some of the ideas around glove vectors was to combine some of the insights that we did with distributional embeddings with some of the concepts of machine learning, with deep learning to build better, more generalizable representations. And fast text is very similar to the traditional CBOW and skipgram, but instead of trying to learn the embeddings at a word level, it does it at a character level, n-gram character level. So this is part of what I'm trying to accomplish with this 10,000-foot level. Again, these things are a lot more complex, and if you find me, we can dive deeper into the differences and the advantages between these different representations. But to show you that this is traditionally how we view this independent representation of how we embed information. And then with addition to this, and I'm going to go very quickly over this, there are different ways that we model this embedding. So traditionally, if we're dealing with sequence data, we would use things like Markov models for predicting the next items in the sequence, and for doing things like classification or regression based on each of the bags of features that we had, even if they were distributional, we would use shallow networks, or we would use other graph-based networks like boosted trees and forest, or different Bayesian methods. With neural, things changed a little bit where we could create deeper networks. So instead of just having a one-layer, logistic regression, we could build feed-forward networks. On top of that, we realized that just concatenating all these word vectors together, you lose a lot of information. So maybe where things progressed from there was the concept of stacking one-dimensional filters, where we take our feed-forward network and we slide it down, and that's where we got this concept of one-dimensional CNNs. We won't go too deep in that. Then on top of that, something that some of you guys may have heard about, and if not, it's definitely worth looking into, some of the advances around RNNs that were very similar to some of the approaches we used with Markov models before for the processing sequences, but they had the added advantage that they work a little bit better with preserving long-term context, whereas the more traditional Markovs had this naive assumption where you only look at local context, historical context, when you're making your prediction about the next step. And the other big advance over the last 4 years was this concept of attention mechanisms. So when we're encoding in these RNN networks, essentially one of the challenges that we had is we would take all our data and we would store it at each step in one vector. And we'd take a whole sequence and we'd provide it one context vector, and we'd try to map it to whatever the other, each uniquely, to, like at the same level, at the same equal uniform distribution to each output layer. And the reality is we know that different input vectors at different steps will have different weight on the output vector, the output streams that we're trying to create. So essentially what attention allows us to do is it allows us to try to learn those weights and what is the influence and how well and it helps align where the input sequence and the output sequence. So these are kind of the things that helped with the improvements we saw before. And to give a little bit of an example of how this all comes together, how many people here know what ELMO is? All right, so I see I have a couple NLP researchers in the room. So ELMO is a more recent paper, I would say past year, coming out of the Allen AI Institute. And essentially what this does is we have a word play in the center here. And let's say we've learned this contextual embedding that embeds all this information of what play means based on where it appears in the past. We still have this problem of ambiguity. Why? Because play could be to play with something, or it could be in this context an actual play. And so how do we narrow that context based on the sentences we see in our training set? And what ELMO essentially does is it takes for each sentence by LSTM network with, I think, some attention mechanism as well, and it encodes for each word in the actual pre-trained embedding that you give it to it additional context based on the other words that appear in the same sentence. So that way it will help narrow down the context that play is not just, in theory, that play is not just the act of playing, but it's actually a matzeget, right? Or hatzaga, see? Language is difficult. And this was a really significant advancement because it has a lot of value in what are called downstream tasks. So if we look at ELMO, we see that a lot of these baseline state-of-the-art tasks prior to ELMO, just by adding this mechanism, they were able to improve accuracy across many different tasks. And this is where people like Sebastian Röder were saying that the ImageNet moment of NLP has arrived. And I don't know how many of you are in the machine learning, deep learning Israel. There was a lot of talk about this a couple weeks ago. And I hate to break it to you, but we're not there yet. And what I'm going to focus on now a little bit is what are the pitfalls? Where do these amazing systems and all these advances go wrong? Well, one of the challenges we have with neural methods is that they tend to learn a lot of superficial correlation in models. So This is one of the traditional examples. They trained a sentiment classifier based on fast text. And in the beginning, they fed it very simple sentences like, I had a great day, or I had a poor day, or it's sunny in Seattle like you saw before. And it seemed like it worked well. But then they tried to feed into it some neutral things that should more or less be the same. And they tried things like names. And they saw if I put my name is Emily, you get this score of 2.2. But if I put in my name is Shaniqua, the sentiment goes down to negative value. So you can imagine now if I'm using these pre-trained embeddings and I don't understand this context or the implications of how they're trained, and I'm using something that's measuring for prison records or maybe for something related to CVs, you can imagine I might now have unintended consequences. Additionally, they have another example where they looked at the context of food. So for instance, let's go get these statements, let's get Italian food, let's get Chinese food, let's get Mexican food, should more or less be neutral. But because the embeddings themselves were trained on a news data set, you can see that Mexican has a different context than Italian, which has a different context than Chinese that's not necessarily related to food. So these superficial correlations are important to keep note of, and they're one of the challenges that we have to think about when we're using these systems in production. Another example is they took a Q&A system and they just asked an open-ended question to see what the correlation is, and they said how many, and the answer is 2. They said what sport? Tennis. What animal? Dog. And this is my favorite one, is or are, and it defaults to yes. That's how you know it wasn't trained on Hebrew, because in Israel, the default answer is no. So that's one. The other one challenge that we have is a lot of these models, while they seem robust on the training sets and the data sets that we train on, in practice, they fail under adversarial evaluation. So for instance, we take that exact same example that I showed you earlier with Tesla, and we add an adversarial sentence at the end here about a guy moving to Chicago in 1881. Now the alignment or the attention mechanism aligns better with Chicago than it does with Prague, because Prague was more vague in terms of the syntax that was used, and my output is Chicago. Now imagine we have something that's checking your grades or whatever, and people are creating adversarial examples. This is something also that we're struggling with. Another example, another challenge we have is semantic structure. So for instance, take that same example of sentiment, which a lot of people, again, I showed it before and you guys are like, okay, great, I've seen sentiment before, this is a solved problem. But it's not really a solved problem. There's one of the state-of-the-art methods for it is the tree-structured bidirectional SDM model. And they show here that if you take a model, input, and you say there's no pleasure in watching a child suffer, it correctly identifies that it's negative. But if we take the exact same sentence with the exact same semantic meaning, the exact same meaning of the sentence, and we apply a different syntactic structure, and watching the child suffer, there is no pleasure, all of a sudden we get a positive prediction. So this is also something to note when just because you get see these articles where it says, you know, we've beat human performance, maybe it's based on the distribution of the samples that we see in our examples. And one additional one, and this is also a real biggie, is around lexical inference. So this is understanding subtext, things that are implied by the text that you or I know based on our context, but aren't necessarily in or understandable by the text themselves. So for instance, if I take the same entailment task I told you before, and I say Jack and Jill climbed Everest, and my hypothesis is there are 2 hikers on the mountain. If we look at the word embeddings, as we were talking about before, I should know based on my embeddings that Everest and mountain are close together, so they should be similar. But in reality, when we actually apply this to models, we see that's not always the case. And this is categorized as neutral, even though it should be entailment. So what does this lead to? So this leads to a little bit, or what are the trends, or where is NLP research going? And there's a big debate of how to handle some of these open-ended challenges within the field of NLP. And it essentially boils down to the question of, is structure a necessary good or evil when building machine learning, deep learning models? And there are two people who are leading the charge of this debate. There are many other researchers, and I don't want to imply that it's just LeCun and Manning over here, but they had a really awesome panel that I recommend you guys watch online if you get a chance, that from February. And the debate essentially goes something like this. You have somebody, both of them agree that in order to solve the issues that we had before, you need to use apply some implicit structure, whether that's from the way that you architect your model or the way you represent the inputs or the features that you're passing to the model to learn. The model's not just going to learn innately. But the question is how much. And LeCun on his side says you have to be careful about applying structure. And he has a little bit of a point, because if you apply too much structure, then the structure that we're applying is based on our own biases, our own understanding, and our understanding is limited based on our failure to be able to process and understand the whole scope of the data. So we're introducing our own implicit bias, and by doing that, inherently, some of the results that you have are going to be wrong based on the structure and the noise in the structure that you provide to the model. Now, Manning says that that's true to some extent, but we need structure can also be a good thing if we think of structure, combined structure, with the data that we're building and training on. And part of the reason for that is if we have good structure and we have a good model and a good understanding, we can do more with less. And if one of the biggest challenges we have with deep learning is if we just feed tons of data, how do we know that it's actually learning or that it's not just memorizing or essentially brute forcing a nearest neighbor at the end of the day? Whereas if we provide some structure and we can demonstrate that it's learning these generalizable patterns that we can validate as humans, then we can take small amounts of data and do more. And those of you who are working on the Microsoft challenge, you might see this. That's one of the challenges with numbers, right? Is I can train a huge deep learning model on numbers based on these embeddings. But traditionally, those struggle with numbers they've never seen before. OK, I am being told I have to move a little bit faster. So where I want to go with this in the last five, and I might take a little bit more because we went a little bit late into my time as well, minutes, is what does structure look like? And so to understand why structure is an issue, I'm going to give you a canonical example. Fruit flies like a banana. So this is an ambiguous sentence. Why? Because it could have two meanings. One is fruit flies, like the insects, like bananas, like a banana, right? Or it could be if I throw an apple, it's going to fly like a banana, right? And so how do we parse and understand the structure? Well, we provide what are the structural options. And the way we do that is we traditionally, from a linguistic perspective, we look at large amounts of data and we see that there are patterns in terms of how words appear. And we apply from downstream to upstream labels to help understand grammars and symbols in order to better represent those patterns. So for instance, we could say, in this case, because the verb is like, and like is not an adjective, then in this case, fruit flies are a noun, versus if it was fruit flies, then flies would be the verb, right? And so by being able to see this, and then we can create constituency structure, and in the end, this gives us some sort of dependency structure that we can use as either features or based on rule-based methods that don't work too well, but we can mix with those to create stronger models. Now, the challenge with dependency parsing by itself is that you can have multiple sentences that have different structures, but have the same meaning. And this is where semantic parsing comes into play. And the simplest method for semantic parsing, where we've had the most success, is shallow semantic parsing. This is semantic role labeling. And what it aims to do is to recover the predicate argument structure between the verb and a verb's arguments. So I'm going to go a little bit faster through this. The idea is to know who did what, to why, where, when, and how. And you can kind of think of this as a predicate is the function, like the verb is the function, And the semantic roles of the arguments are kind of like class-typed arguments, which as a developer, that's very valuable for me because when I code, I have functions and I have arguments. So an example of this, and I don't know how many of you guys know Schoolhouse Rock. Look it up if you're interested. But the concept is like if somebody bought flowers for, Mr. Morton bought flowers for Pearl, bought becomes the predicate or the function, and these are the arguments that then we can process. The next layer of semantic representation says, okay, that's great, but it's shallow, and we're only looking at verbs, and there's more structure than just semantic structure than verbs. So what AMR tries to do is it tries to provide a representation that abstracts out the actual structure of the sentence. And in this case, if I have 3 sentences here, the soldier was not afraid of dying, the soldier was not afraid to die, the soldier did not fear death, they get represented in the same graph, so that way we encapsulate the same meaning. This is in no means a solved task, and there is a parser for it called JMR parser, but it has, you know, about F1 of like 47. So I wouldn't rely on these things, but they're interesting, and it's a very valuable representation. It's used a lot in things like multi-document summary generation, event generation, text generation. So the last one, and one of the areas that I've been focusing a lot on, is called semantic dependency parsing. And the advantage of semantic dependency parsing over AMR is that it preserves the sentence structure. It provides, unlike SRL, a deep parse of all the predicate argument structure. And it provides semantic generalization, meaning that I will have the same SDP graph on top of my different sentences if they have the same semantic meaning. Now, there are a couple of different schools of thought on how to tag these. I'm not going to go too deep into them. You can follow up on them after the talk if you're interested. But the 4 are universal dependencies, DM, PAS, and PSD. And each of these are different grammars made by different linguists that provide this type of structure. And they provide interesting features. So I am planning to give a demo. I know I'm fixed on time, so I'm just going to go very, very highlight through this. At Microsoft, we provide like a lot of tools to enable developers, especially data scientists, machine learning engineers, to get started at experimenting and get their work into production very, very quickly. One of the tools is Data Science Virtual Machine. I'll go quickly through this. Essentially, it enables you to do elastic scaling, comes with GPU environment, GPUs, NVIDIA GPUs. Also, some of them in the future could link up to some of the stuff that we're doing with FPGAs. And we also provide a new service that was just announced last week that helps with each stage of the data science machine learning process, from preparing data all the way to deploying. Sorry, if people are taking pictures and stuff, go for it. And one of the things, I'm not going to show it right now because I'm cut on time, but I put together a demo based on what's called Nerbo parser. So Nerbo parser is a parser for semantic dependency parsing. But one of the challenges with it is it's a C++ implementation on a framework called DyNet that's very hard to actually practically use within your own engineering applications. As part of my role at Microsoft, I sat down and created a Docker service around it that provides Python bindings that you can use. And I also provided instructions on how to get started with that and use it either locally or on Azure. I have a repo that you can come to me and ask me to use at the end. And I'll open up with my last 30 seconds for questions. Bueller? No, sorry, just kidding. Questions? Charlotte? Yes.
I wonder how you use MCP.
So one of the ways that, sorry, can you guys hear me? So one of the ways that you can use SDP is you can use it two ways. One is to understand what are these implicit structures based on tagging your data, and then you can provide that as features. Or you can try to use it to understand, okay, based on this semantic structure, I should break down my problem into this subcase. This semantic structure, I should break it down to this subcase. There are different, depending on where you fall on the implicit, explicit. And again, a lot of this stuff is still research development, but I wanted to provide some of the advancements that we've made from a research and development perspective to something that you can experiment with in actual engineering production setting. Okay, thanks guys, really appreciate it.